Hi all, I'm very sorry not to be there. Thank you for inviting me. I'm very happy to talk with you. And today I'm going to talk about this work with Mark Podolsky and Arturo Garamillo. We are going to talk about how to use Stein's method to prove stable convergence. So what is that about in particular? Well, first of all, we are going to formulate the problem. So we are going to explain which are the guys we are going to work with. We're going to consider high-frequency statistics of Levy processes. And then we prove asymptotic mixed Gaussianity for this particular object. So I don't know how familiar you are with mixed Gaussianity, but basically we're going to prove Gaussianity, and we're going to say that the variance is going to be a random object. How can we do that? Well, using some Stein characterization that we're going to construct ad hoc for the problem. And it's very nice, I think, what we're going to do, because we're trying to understand how to use the Stein method in a very general way. So we are going to use Stein's method to provide a criterion that ensure stable convergence of our processes. After that, we're going to assess, we're going to provide a quantitative statement as well, so we can assess how fast this convergence is happening. And we're going to talk just for a little bit of some ideas that we use in order to prove our main results. But really just some key ideas about Stein's method. So, to start, we want to understand which statistics we are considering. And here, can you see my pointer as well?
Yes.
Yes.
Very good. Very happy about it. Okay, today in this talk, I'm going to present an easier case where G, our weighted statistics, are just statistics coming from asymmetric alpha stable Levy processes. But actually, in the real work, if you go and see, give a look to the paper, we consider a very general stable process, and instead of having G a function in two argument and where it only depends on some increment on X, in the paper we consider several increments. So in the paper we consider these kind of statistics in full generality, but here, in order to make the talk a bit easier, we decided to work on statistics of this type, which are already centered, which is always nice. And we want to understand what's the asymptotic behavior of these statistics. In particular, we are going to see, spoiler, that they are going to converge to mixed Gaussianity. They are going to converge stably. So, of course, we are going to introduce in detail what is this stable convergence. So far, let me say that it's basically a formulation of a weak convergence. And after having proved this stable convergence, we want to show also a quantitative version of it. So we want to say how fast this convergence is happening. Before doing that, we want to discuss what we already know. So what's the state of the art? Well, there is a lot that has already been done, especially from the Luxembourgish school over here. A lot of references here come from three people: Giovanni Peccati, Ivan Nordan, David Noalart. It's always the three of them and like some subset of them. And maybe sometimes there is someone else joining. But basically what I really wanted to say is that there is already a lot of literature on stable limit theorems, where they prove this kind of stable convergence, which is not yet quantitative in the first point I brought over here, while the second step is to go to quantitative results so that we can understand how fast this convergence is happening. And the third step would be to prove some Edgeworth expansion. What does it mean? Well, it means going a bit farther, and so considering the second order expansion to understand what's the rest term if you already studied the central limit theorem and you already studied the fluctuation. And so you want to understand if you can prove that also the main term converge to something, and you want to understand what's that something. Here in this talk, we are going to consider in particular the first 2 points, the stable limit theorem and the quantitative result. And the Edgeworth expansion is still an open problem that is interesting and can be well, it's an open question, but I would like it to be a work in progress. Who knows? This is going to be understood in the next few days. And what's really important here, what I wanted to say is that in order to show our result, we are going really to introduce a criterion to obtain stable convergence. And to do that, we are like constructing a Stein method ad hoc for the problem. And it's important to say that a universal Stein's method is something that it's completely unexplored so far. Why? Well, because it's a bit complicated to construct a universal Stein's method, because when you talk about Stein method, you need to be able to guess more or less what the variance that you are going to obtain in your asymptotic Gaussianity. And so you need some extra information about the law, which is something complicated to have in general, right? That's the reason why it's a bit complicated to use like Stein's method all the time. But if you are able to prove this criterion that we are going to see in a bit during this talk, then it will be easier to understand the rest of the proof, and it will be easier to say that it's possible to recover this mixed Gaussianity. Another thing that I wanted to tell you is that if you see here, the first point, this stable convergence, all this literature that is available so far, always emerge from some Gaussian processes. And so what I think is important here in this talk, in this work, is the fact that here we are considering a Levy process, and we do not need to embed anything in a Gaussian word, okay? And after all this introduction, all this about the background, we are finally ready to introduce what the stable convergence is more in detail. So I don't know how familiar you are here. I provided just the definition. This notion of stable convergence is due to Renyi. And what's important is that you start with a Levy process, X. And then you consider the sigma algebra G that is generated by this Levy process. Then you have a sequence of random variable yn, and you want to say that this yn converge stably in law to some y. So there are some technicalities that one has to consider. First of all, you have to consider an extension of the probability space on which you are, and y is going to be on the extension of the probability space. But what's really important, and I want again to highlight this, is the fact that the stable convergence is going to be with respect to some particular sigma algebra that is generated by X. And so this convergence, this concept of weak convergence has to be true for any continuous bounded function small f, okay, but also any bounded G measurable random variable capital F. And you see that this is a definition that really reminds the classical weak convergence in the case where F is just the identity. But it has to be true for all the G measurable random variable capital F. This was the definition of stable convergence, and once we have that, we can move further, and we can introduce, as said before.
And what is a prime on the right? Why it is E prime?
The expectation in the new probability space.
It's because we are now on the extended space. You see that this random variable y is defined on the extension, and as you have this probability p prime, with respect to this probability p prime, you can construct the expectation prime. And so you are now in the expanded space.
And then you can put prime on the left as well for free.
You can put prime on the left. No, because the original, it's like you are considering this extension space. It's like the closure of the original one. So all the random variable yn are defined in the original probability space, you see? And the original probability space, it's true that you can restrict.
Yes, you can, yeah.
Sure, yes.
You don't forget
It's
about prime.
True. And yes, this is just the definition, and then you move to what is our criterion. that is written over here. And what are we doing here? Well, here we are saying that we have some random variable Sn. Here you see it's a very general framework. Here we do not have, like in the original random variable, we do not have any dependency in the Gaussian word, on the Gaussian word, you see. But what's important is that you start with something that is in L2 and you have already an idea of what the variance is going to be. Because this V square is really, it's going to be the variance. And you have to know that this is going to be something in L2. So what you can say is that once you are able to show that this convergence holds true, and this is really the criterion that I was introducing before, once you have the criterion, then you get the mixed Gaussianity. And here there are a couple of things that I want to remark. The first one is the fact that in order to prove this result, we use Stein's method a lot. And if you are familiar with Stein's method, we are going to see it later, but if you are familiar with Stein's method, you could ask, oh, well, but isn't that weird, the fact then that there is no convergence rate? We don't have, from here, we do not have any intuition about how fast this convergence is happening. While on the other side, Stein's method generally provides some intuition, some quantitative intuition. Why is the case here? Well, because we are proving just stable convergence. And you see, in this criterion, we are not saying anything about how fast this quantity is going to zero. So as the stable convergence here is not metrizable in general, it makes sense that even though we are using Stein's method, we do not get any quantitative assessment so far. We can still, we'll see it later, improve this theorem in order to get something quantitative. But before going on, I want to show you the fact that, well, this theorem is useful. You can use it. And how are we going to use it? Well, first of all, I've introduced one problem in particular, which is considering high-frequency statistics of the Levy process. So, of course, I'm going to use this criterion to prove the stable convergence of high-frequency statistics of the Levy process to start. This is the first example we are going to see. And here you are. We have defined before the GTN, where we are considering statistics of the Levy process between 0 and capital T. Here we are just saying that T can be whatever you want. Why not taking just the interval between 0 and 1? Then you understand what's the variance, and applying the criterion that we have just seen before, it's possible to show that the guy we were working with before is indeed in the limit a mixed Gaussian with a variance that is written over here, and it depends very much on the function g we started with. And that makes sense. That's the first thing. But then we would like to have something more. We would like to have at least another example to show, okay? And I think that a nice example to show is something that is actually already known. It's the fact that if you start with a Gaussian process X and you have a sequence of Skorohod integral Sn, then you know that this Sn converges to a Gaussian. And this has been proven by Ivan and David in 2010. But the proof was quite complicated. It was quite long, and you had to prove, well, it was long. And, well, it was based on the fact that if you have these two conditions, then we were able to prove this asymptotic Gaussianity. And here what we want to do is to say, okay, for us it's the same. We can prove as well that these two conditions imply the stable Gaussianity. So it's nothing new here, but I feel that this is a way shorter and nicer proof, in the sense that really once you know that you have these two conditions, 1 and 2, the proof is really 2 lines. Because in order to get the stable convergence with the previous criterion that I showed you, what we want to understand if it's just if this condition holds true. So this is the condition that we want to check, but for Sn being a sequence of score-hot integral. Okay, knowing that UN these symmetric functions against no matter which element of the Hilbert space we are considering is going to go to 0 in L1, and while if we consider the Magnum derivative of the same score-hot integral, this is going to converge in L1 to some variance capital sigma. And using this, the proof of our criterion is really short. We start with this guy, and we have said that Sn are the score-hot integral. So we replace the score-hot integral in the definition of Sn, and we just use integration by part. Now, after having used integration by part, you see here we have the derivative of f and h first, so we have the derivative of f here, the derivative of h second here. We have two conditions. The first condition tells us that this guy is going to go to 0. The second condition tells us that here we are going to get the convergence to sigma. So the condition is already true. You see here, it's really one line in order to say that this first term is really just condition 1 and it goes to 0. And in the second term, we remove also what we had here in the right part of this criterion. And it's again one line to show that it goes to 0 because of condition 2. So we have checked. Are there any questions? Is everything good?
Yeah, it's all good.
Okay, thanks. And so really in 2 lines, we are able to prove that the criterion is actually satisfied. And thanks to this theorem that I showed you before, we are able to show the stable convergence in a very general setting without any assumption needed on the initial Gaussianity of any process, which was nice. But then, as I said before, so far we don't have any intuition about how fast this convergence is happening. And we want to understand how fast this convergence is happening. So what we can do? Well, here, this is the answer about how fast the convergence is happening. Again, we are just in this talk considering the easier case where you have a symmetrical alpha stable process. In the case where, in the general case where you have a general Levy, it's not as easy to read the rate, but this is a representative statement in the sense that it depends the distance, so how fast this convergence is happening, depends a lot on alpha. Alpha dictates the behavior of our process. And so in particular, when alpha is between 0 and 1, which is what I wrote here at last, the convergence is really fast. Is n to the power of minus 1 over alpha, 1 over 2 is really the benchmark, is what we wanted to have. And for alpha equal to 1, you see, it's tautology. There is an extra logarithm that you use all the time when you get in the threshold. And for alpha, because if you replace alpha equal to 1 in this result over here, you would recover n to the power minus 1/2 again. So really, it's just that the special case where alpha is equal to 1, it's the threshold and bound, something happened and you lose the logarithm again. It's because of an integration. What's also interesting here is that, well, here we are considering the case of an alpha stable, right? But for alpha equal to 2, we should just recover what happens for a Brownian motion. And the Brownian motion is general something that people studied before. So it should be something known. But if here we replace what happens for alpha equal to 2, well, 1/2 minus 1/2, and there's nothing to say. It's n to the power 0, so it's a constant. That is not even going to 0. And so it seems false. It seems that there is a problem here, right? Well, it may seem the case, but one important thing to remark is that if you add symmetry, so if you know that the function g you started with in the definition of the statistic is symmetric, then it's possible to improve what happens for alpha larger than 1. And again, it's possible to recover exactly the same case as for alpha smaller than 1, which is n to the power minus 1 half, which is the benchmark, which is something that makes us happy. So here what we are saying is not that for alpha equal to 2, so for the Brownian motion, it does not converge. What we are saying is just that it does converge, but you need to add symmetry. And so the question is, well, do we really need symmetry I mean, for the Brownian motion case? Yes, and in order to convince you...
Excuse me, could you
Yeah.
ask, what is special with number 5 here?
Yeah, I was about to ask the same question.
For the derivatives, you mean? It really it's really technical. It really comes from the fact that we apply Stein's method that gives you like a second derivative in H, so on the test function. And then we applied also like Taylor approximation. And in order to obtain the nice rate, in order to show that everything goes to 0 as it has to, we have to derive 3 times.
Okay.
And so in total, we have to derive 5 times. And so we need to say that these derivatives up to order 5 are bounded.
And what is conjecture? Whoa.
If it's optimal or not, if it's possible to remove it.
No, the answer is it shouldn't be optimal because 5 is artificial here.
Yeah, exactly.
It
I
should be,
think that
2 is enough?
I think that the optimal should be 2.
Okay, good.
Yeah. Thanks. Very nice question. Happy about it.
Okay. Why not?
If you have some other question, please stop me, because I'm sorry about not being there. You see, while you are there, you can see from the face if something is not clear or not. While being away, it's more complicated. Please stop me again if you have questions, okay?
Pleasure.
Why 2 and not 1? You need Lipschitz.
No, 2 is needed.
Oh.
No.
Yeah, because you really need to apply Stein's method, and we are going to see later that in order to apply Stein's method, you have to work with the derivative of order 2.
So it may be an artifact of the proof, right? So here you want to prove this for Lipschitz continuous function. So lambda should be 1. L, not lambda.
L. Well, I think that if you have something L smaller than 2, smaller strictly, there's no way you can use this method at least.
Yes.
I have the feeling that you can still use Stein's method for a L equal to 2. It's just that later on you should understand how to get rid of the negligible term in another way. But the term with where you derive twice is not going to be negligible. It's going to be the main term providing the variance. So for that one, there is no way you can get rid of it if it's the main part.
Sure. So you need Lipschitz for the first derivative, so which is more than typically
Exactly.
Yeah. Okay.
So this metric is it the Solotarev distance?
Is what?
Solotarev distance.
I didn't get you. If I can consider some other distance, you mean?
No. Is this not known as Solotarev distance or something like this?
No. There is an idea. So this, I think, is it's from the ages of last century. What is known? There is a characterization. You know, characterization of Poisson distribution. Yeah.
Yeah.
There is another characterization of the normal distribution. And in terms of this characterization, you can study convergence rates, whatever. It's from the age papers from the ages, from the conventional normal distribution.
No, I understand this, but I think the metric.
Stein methods exactly. So
yes, I understand that.
Yeah.
I understand that. No, I'm saying that this metric I think coincides with, or is very closely related to the Solotarev distance that controls Vashtan distance. There's some laws of it, obviously, but
Okay, yeah, you're naming the
I mean, you lose convergence
Yeah,
rates. I
sorry.
mean, you pay a price, but I think you can control, you can bound them, certainly. Okay, anyway, sorry.
No, don't worry. It's nice. I like it. Okay. So yeah, here what we are saying. So coming back to the order we actually get is that for alpha larger than 1, we really need something more. We really need symmetry. And the question is it the case for the classical Brownian motion? What do we know? And in order to answer, we can consider some other way of getting the result. I'm sorry, I don't know where to put you guys. Let's say here, we get it, okay. Let's say here for now. And this is a theorem from Jean-Jacques Code that tells us how to get another criterion to get a stable convergence. Be aware of the fact that the previous one, I proposed a simple case where we have like only one increment, but it works exactly in the same way also for a several increments in G. While here with this method of Jean-Jacques Code, you could not directly apply the same criterion in the case where you have multiple increments. This was the first thing. Second thing, here the criterion is a bit different in the sense that you have to check these three conditions. So you have to check basically that the square moments converge to the variance, which is the first point. The second point is that if you put your Z, so the variable of interest, against no matter which continuous martingale, because this has to be true for any continuous martingale, it has to go to 0. And the third one is saying basically that the moments that are more than 2 are going to 0 by order. So what happens is that you can ask yourself what's happening for alpha equal to 2 and for alpha different for 2. And if you want to prove our theorem using this criterion, you can prove condition 1 and 3 for all the alpha, and it's really easy. What's more complicated is to understand what happens in this condition 2, because this condition 2, for jump case, so for alpha between 0 and 2, but 2 excluded, is true, just because of the fact that you have the orthogonality between the jump case and the continuous case. And so the product bound factorize, and this is 0, and life is beautiful. But if you consider the case alpha equal to 2, well, this is not true. This doesn't hold, not even just for M equal to Brownian motion itself, because you have the Brownian motion against the Brownian motion, and it does not go to 0. And so you see, in general, this condition is not true, and in general, you cannot apply this theorem to get the stable convergence of the Brownian motion. But even in this case, if you add the symmetry of G, well, again, the second condition is going to provide the convergence to 0. And so you can actually apply this theorem as well in the case where you do have the symmetry of G. So coming back to our case, what we are saying is that also from here, you can see that for alpha between 0 and 2, but with the alpha equal to 2 excluded, you can apply this theorem and you can get the stable convergence. But even in this case, for alpha equal to 2, it seems that it's really important to have the extra symmetry. And so we can go back to our case and we can go back to our result saying, okay, we have understood how fast this is happening, and we have understood that this extra symmetry is going to help us to prove that the convergence is happening fast. But here, for the last time, I swear, to tell you that this that I'm presenting today is an easier case where one has just stable process. If we consider a general Levin process, it's not as easy as that, because again, we can understand that some kind of symmetry is needed, but it's not enough just to say that the function is symmetric in the second component. We need a condition on the symmetry that is in connection, a connection between the behavior of G and the behavior of the process X itself. So you can ask more on the process so that you can ask a bit less on the symmetry of G, or you can ask more on G and less of X. But what's really happening is that you have a mixed condition between G and X in the general case for a general Levin. But here, life is beautiful, everything is nicer. Why? Just because we have the stable case, and so the condition is only on the symmetry of G. We arrived here, we can see that the convergence rate is almost always the benchmark, but in the case alpha equal to 1, where we lose a logarithm. And then the question is, how? How is it possible to get this result? As I said 2,000 times, the most important part is the fact that we use Stein's equation. So we are using Stein's equation, but a particular one. Here I've written the general Stein's equation. But we are going to use, in our case, a random version of Stein's equation. Indeed, here in the first case for the normal Stein's equation, what happens is that you have some test function, which are these psi belonging to some class. You want to understand how far away they are from a Gaussian with some particular variance. And instead of writing this guy, you can consider the solution of the Stein equation. So you write the distance as a function of the first and the second derivative of the solution of the Stein equation. But for us, this is going to be a bit more complicated because we are proving the convergence to a mixed Gaussian. So this tau that you see over here for us is going to be a V that is random. So the variance is going to be random. And it means that basically the equation that you have here written, the classical Stein equation written here, for us is going to be useful only once you take it in L1. So we take the Stein equation, but directly with the expectation from the beginning. And so what happens is that if instead of having X, we plug our Sn, we are checking here what's the distance between test function computed in Sn and test function computed in the Gaussian in expectation. And so you can see down that the role played by tau is now played by our random variance v squared. So what we want to prove is that the distance written here, which is the distance between our random variable and the limit, is smaller than some quantity that I've written here as Rn, which is really going to be the convergence rate. And it will be dependent on alpha. Okay, for alpha smaller than 1, this is always going to be n to the power minus 1 alpha. Otherwise, for alpha larger than 1, it depends on the fact that we do have the symmetry or not. So this is the general idea on how Stein's method is going to play a role in our proof. And that's basically all I want to say about the proof. And the second ingredient that I want to provide is just the fact that we use Stein's method and a key K approach. Again, I move you guys over here, or maybe here. Yes, not too much. I move you here. And the second ingredient that I want to explain is the fact that we need to have something, we need to remove in our process the dependence on some particular increments. Why? Well, because it's going to be important, the fact that we work on a sum. On each sum, G depends, first of all, on X computed in some particular point, and then on the increment between I and I minus 1 over n. And so we really need to replace our original process X with another process that behaves exactly in the same way everywhere, but on the increment. This is the idea. And on the increment, what do we do? Well, at the beginning, we thought, okay, maybe we can just cut it off and not having anything at all. But actually, well, we had problem later on. We really need to have something else. And what happens is that we can replace it. We can replace what happens to the original problem with another process that is independent from the first. So the idea is really to replace the original random variable, the original process X, with the X minus I that behaves exactly as X everywhere, but on the interval. And on the interval, we have an independent copy of it. Starting with the definition of this new process, one can define all the objects that we had defined before that were dependent on X, and now they will be dependent on X minus I, on this new process. So we get a new S, a new variance, and so on. And the main point is going to be the fact that this expectation is now 0. Why? Because the Z we started with are centered. So the conditional expectation are 0. But the problem was that we weren't able to take the conditional expectation of Zi because we had here something else depending again on the very same Zi. And now with this small trick that I wanted to present just because it's nice, one can use Tower property and take the expectation of the conditional expectation with respect to Zi, but now the new process is independent from that sigma algebra, where you have like what happens everywhere else. And so what happens is that you can just take the conditional expectation of Zi alone that was centered. And so now this is 0. And why is that important? Well, because as this expectation is 0, you can remove it and you can add it as you wish inside the problem you started with. So remember that we wanted to show that this was going to 0 at a certain rate. And as you can add and remove this expectation as you wish, you can remove here the derivative of h in this new process. And so now the idea is just to use, well, you have h first in one point and then h first in another point. Well, the idea is to use Taylor approximation. And so if you have a Taylor approximation from this guy, you are going to get a second derivative in more or less v. Of course, the technicalities are going to be a lot because then you have to be able to move from v to v minus I, from s to s minus I. You have to understand, you have to consider a lot of terms in this Taylor approximation, but the main idea is really this one. It's really the fact that the main term is going to be given by the second derivative of h computed in v, and then you have a ton of error terms that you can prove being negligible using even iterating this trick, this K approach that I've just shown you. But then if this is the main term, here you have basically something that it's almost the proof. It's just that instead of having this Zi, you want to obtain the real variance. But this is finally going to be just some kind of Riemann approximation. And once you prove this final step, you can prove, you have proven basically the criterion of the convergence we introduced before. And so you have proven all the theorem. This is really like the proof of the main theorem in a nutshell. 2 key ingredients, Stein's method and K approach. And I wanted to at least name them to you just because I think it's nice. It's a nice way. It's an elegant way of proving this kind of result. And that's all. I conclude by showing, well, by saying again what's the take-home message. So what do we have? Well, what's the point here? We have given a general criterion to prove stable convergence that I wrote twice. Sorry about that. A general criterion for proving stable convergence toward a mixed Gaussian without saying anything about the original random variables. Actually, they just have to be in L2. So it's nice. And we have shown some example of, well, of things that now converge stably toward a mixed Gaussian limit. One of them is indeed the problem we started with, which are just high-frequency statistics of some Levy processes. And another one was okay in a Gaussian setting. And in this case, considering the high-frequency statistics of these Levy processes, we have also seen that they converge stably towards a mixed Gaussian, okay? But also we have seen how fast this convergence is happening. So we have assessed the rate of this asymptotic Gaussianity through a Stein's method. Adding some extra condition on the symmetry, we have proven that it's possible to improve this convergence rate and obtain something that was indeed just the benchmark in the case of stable process. More complicated for a general Levy. And that is all. The talk is based on this paper with Mark and Arturo. Thank you all for the attention. I can see you clapping, I cannot hear you.
Thank you, Chiara. Do we have any questions?
Yes.
Can you go back a slide, please? And then... Do you think, yeah, no, that's okay. No, that one was okay.
This.
Yeah, that's fine. So do you think the symmetry in G that you need is because essentially you would have had to compensate with something? And when you have a symmetric spectral symmetric process, when you have a symmetric G, essentially you don't need this compensator. Is that like the reasoning behind it, like, or?
Yeah, it's more or less really, yeah, it's really the idea. The point is that when you know that you have symmetry, you see the trick here that we have done for the K function. When you have symmetry, you can say that not only this guy, but you have some other things that are just going to be zero. In particular, you can say that Zi times the increment are already zero. Because when you use Taylor approximation, well, in the Taylor approximation, you are going to obtain the increment, right? So you really have the increment times Z. And if you have the symmetry, this is already zero and you can forget about them. But if on the other side, you don't have this symmetry, what you have to do is basically to repeat the trick of the K function. But now, instead of having only some increment with respect to I, you are going to have some extra increment. So you have, as you were saying, basically you have to compensate by adding something else. And this something else are some, like, you are adding back some extra increment with respect to some G, but then you have to remove them again. And these things that on one side seems to be a technicality, so it seems that it should be negligible on one side. On the other side, it's not better. It's going to converge to zero, but it's going to play a role inside the Rn, and this order in the case of the stable process is indeed n to the power 1/2 minus 1 over alpha. So for alpha going to 2, this is exactly the guy providing the problem.
Mm-hmm.
You see, but if this is zero from the beginning, the increment against Z are zero from the beginning, you don't need anything at all, because you are already there. You see, there's nothing that you have to bound. It's not even a matter of having a sharp or a bound or not. It's really zero.
Yeah.
See? But then, yeah. But then maybe there is also a smarter way of compensating in the case where this is not zero. I don't expect a miracle to be there when alpha is close to 2, though.
Okay. Well, thank you.
Thank you. It was a very nice question, actually.
Any other questions? In that case, thank you again.
Thank you.